Hi, so this is a talk on a new type of chosen ciphertext attack we developed in order to exploit a vulnerability we found in Apple's iMessage protocol. iMessage is, of course, Apple's end-to-end encrypted messaging protocol. It was first developed in 2011. It is now deployed on about 1 billion devices and handles a peak of about 200,000 messages a second. And it was really sort of the first large-scale deployed end-to-end encrypted messaging protocol. Prior to this, most messaging was sent, in fact, over SMS, which of course has no encryption whatsoever. And it's sort of interesting that we kind of think of messaging as not being that important. Of course, these kind of things are actually relied on by activists and oppressive government regimes and stuff to sort of protect themselves. And sort of from a technical standpoint, it's interesting because it turns out that iMessage, the encryption protocol, isn't actually just used for messaging. Turns out that Apple uses it in handoff, which syncs the state on your browser from your desktop to your phone. You could see why you might want end-to-end encryption there. And then Apple uses it in one other undisclosed product that they mentioned existed when we were discussing mitigations with them when we disclosed the attack, but they wouldn't actually tell us what it was. I'd like to think that it was the Apple Car, but realistically it was probably something involving the iWatch. I don't actually know. So what do we mean when we say end-to-end encrypted, right? Well, if you're sending a message from one device to another over a network or using a server, right, you can basically have 3 options of how you can send it. You can use no encryption, in which case your message is sort of exposed. You can do what I think we'd all come to expect. You can do transport encryption, where the link from the client to the server and from the server to the recipient is encrypted, but the message itself is not. So it's exposed on the server. And then, and these are not mutually exclusive, you can do end-to-end encryption, where you encrypt the message on the device, and it is not decrypted by anyone. It cannot be decrypted by anyone until you get to the recipient, right? And this is sort of the gold standard. This is what iMessage sought out to do. This is what Signal and WhatsApp do. This is even what Facebook Messenger now has a deployed version of doing for only on phones. And what we developed in this case was an attack that for some types of iMessages reduces the security from the setting where you have end-to-end encryption over here to the setting where you only have transport encryption, right? Because at that point, then the message is only protected to the extent that you can't break the links on the encryption or that you can't get into the server. And this may not seem that significant. You may think that that's a fairly secure scenario. I think a couple of the other authors in this session might disagree with you about trusting TLS, at least as is. Okay, maybe that's not that big of a threat in your head. And you're probably thinking the server here is probably pretty secure. It's like 1 or 2 devices, boxes. It's not going to be that easy to get into, and no one would care. But for a cloud-based service that's handling, hundreds of thousands of messages a second across a large geographically diverse area, this schematic is really inaccurate, because that little box there is actually something far more complicated, right? You might expect, to involve multiple servers or even multiple data centers, and you maybe you should be a little skeptical about your ability to secure something like this just off the bat, because there are a lot of things that can go wrong. And for those of you who recognize where this slide is actually taken from, you should be incredibly skeptical of your ability to secure this if you're the kind of thing that nation states are interested in, because they have very well-resourced, very smart, motivated attackers who will go look at your architecture and gleefully point out that, in fact, you have no encryption in one particular step, and they can read all of your messages. In this case, this diagram is actually taken from something against Google for Gmail, but funnily enough, Gmail doesn't have end-to-end encryption, but nonetheless, these kind of attacks apply. You can imagine someone doing the same kind of thing to an end-to-end encrypted messaging system, right? So this is why you want end-to-end encryption, right? It really is important, right? So how does iMessage get this? iMessage is really the simplest protocol you could probably think of. There's no crazy properties for forward security as an OTR. There's no overly complex triple or quadruple or sextuple Diffie-Hellman handshake, whatever it is that Signal/Oxalotl is up to these days. There is simply just a directory server that distributes public keys, and then you encrypt your message under the recipient's public key, and you send it via Apple's push notification network. And the question, of course, is this secure, right? There's some questions about, how Apple distributes keys and does device registration, and we examined that, found some flaws that other people had discovered and confirmed they were still there, and found a couple of other ones. But the main question is, what is this encryption, and is it actually secure, right? And so, interestingly, this is actually documented. Apple did, in an iOS security white paper they published a while ago, give you a very short, paragraph description of what their encryption format is. And that format is very simple. An encrypted iMessage consists of an RSA ciphertext encrypted under the recipient's public key. The ciphertext is 1,288 bits, so you can't fit a full message in there, so they don't. They just encrypt a symmetric key, and then they encrypt the actual message using AES under that symmetric key with AES in counter mode. And then for good measure, they signed it with the sender's public key, right, with an ECDSA signature so that you know who it came from. And so the interesting thing is, from this one paragraph description, you can actually conclude that there are several things wrong, and the protocol is in fact cryptographically broken. Right? This is all you actually need to see to know that, right? And so what's the catch? What's wrong? Well, first of all, you may remember that you ought to be using authenticated encryption these days, right? And that means you use AES in GCM mode, maybe you use OCB, maybe you just use an HMAC, but this is AES in counter mode, right? So it's not an authenticated cipher suite itself. And I'm not hiding anything in the schematic here. There is no HMAC in here anywhere, right? And some of you may be thinking, well, but there is a signature, right? And I actually suspect maybe one of the engineers at Apple was thinking this too. And that's authenticated, right? We're signing the thing. We know who it came from. That's authentication in the standard definition, right? And indeed, in most uses, you might be able to think that. But it turns out that, remember how I said there were two things wrong here? Well, the second one is that there's an identity misbinding attack, which means that if Alice is sending a message to Bob and I grab it, I can strip off Alice's name from the envelope information, strip off her signature, put my name and my signature on it, and then send it to Bob, and Bob will think it's a message from me. And this seems sort of like a pedantic objection. It is a type of flaw in protocols, right? But it's not really clear what this would do to the confidentiality of the protocol, right? Because there's no way you should be able to use this to actually read what's in that message. You've just managed to send it to Bob and made him think it came from someone else. But the thing is that if I do this attack, I'm not limited to just replaying the exact message I got. Because once I've stripped off the signature, I can do whatever I want to the ciphertext and then sign it as if it came by me. And so this means the ciphertext is malleable. And this should actually worry you, because if you remember, if any of you have taken a cryptographic class, there is this very complicated definition of indistinguishability under adaptive chosen ciphertext attack, which is sort of the basic gold standard for what you want for a secure encryption scheme. And it basically says that if you have malleable ciphertexts, you can't meet this definition. And great, so now we know that iMessage is technically textbook broken based on merely the nice paragraph description they gave us. But it's not really clear how you are going to exploit this, because this game involves an attacker who has Oracle access to be able to decrypt any ciphertext they want, to just literally ask for the decryption, provided it's not the one they're challenged on. And the natural reaction to those of you on the system side of this or anything is, well, that's unrealistic. No one would ever build such a system, and if you did, you deserve to get owned. Well, okay, so how do we go about translating this into practice? So consider something that's maybe a little more plausible. Suppose instead of having an API that said, hey, what's the decryption of this message? We had an API that said, hey, is this message valid? Is it the right link? Is it encoded properly, et cetera? And this still might seem a little unrealistic, because again, why would you add that API? But it turns out, in fact, that this actually does happen, just sort of indirectly, right? This is an example of an actual stack trace someone posted to Stack Overflow going, hey, why am I getting this? And it turns out, right, that this is an example of a padding Oracle attack. This system, it's probably encrypting a cookie, is vulnerable to exactly this type of thing. It's called a format Oracle attack. And it turns out that you don't directly have to have an API that exposes this, right? The server wasn't very well configured. It's reporting stack traces and such. But you can infer that there was an error maybe by a side channel, by timing, or by the fact that the server didn't do the next step that it was supposed to in the process. Like say, it's supposed to email you after you submitted something. And so this attack is actually practical, and it's used to quite a good degree of effect. And so seemingly we have some good news here, right? We can come up with an actual exploit, except for the fact that there's no padding, right? This is AES in counter mode, right? AES in counter mode is a stream cipher. You generate a bunch of random bits using AES, and you XOR them with your message, right? And this is very good for us from the point of view of doing malleability, because if you want to flip an arbitrary bit in the plain text that's being decrypted, you just flip the corresponding bit in the ciphertext, right? You don't know what the value of it was, but you know you flipped it. But this also means there's no padding, right? So we can't mount a padding Oracle attack, right? We also can't mount other variants of this that people have developed. There was an XML one, there's a font encoding one. None of these really work directly here. So it's not exactly clear what we should be doing, right? And in fact, in order to actually exploit this, in order to get a proof of concept, we're going to have to develop a new type of format oracle attack, right? And unfortunately, this is where we leave the realm of what Apple nicely documented for us, because we need to do two things to get a format oracle, right? We need to figure out some format that we can exploit and how to flip it to actually get errors that tell us what the contents of the ciphertext are. And then the second thing is we need to actually be able to do that remotely, which means we need to see the errors somehow, right? And this sort of begs the question, what is in this box, right? What is the actual format? And so this isn't documented, right? There was a sort of partial reverse engineering done by Quarks Labs a while ago. They also found some issues with how keys are distributed. But we basically had to finish this out, right? You have to go stare at the raw messages and like write a bunch of Python code to parse them and figure out what's going on. And if you do that, and it's a painful process, you recover basically this diagram. And this is a fairly complicated format, actually, right? It's at a high level, it's a Gzip binary plist, a binary plist being this proprietary sort of format Apple uses for serializing data. And it's kind of interesting because they went to a lot of trouble to save space in this, right? Because the push notification network didn't want to deal with large messages. So they compressed the thing, and they actually stuffed part of the message into the RSA ciphertext, right? Because I said it was 1,288 bits. You're only putting a 256-bit AES key in there, so you have some leftover space. And so that space actually has part of the message in it. And the RSA ciphertext, by the way, is actually correctly done. It's RSA or EAP, and you can't mess with it. And so this is just sort of interesting, like looking at it. It's not quite clear what we can use for a format oracle, but if you start looking, you notice that this might be, we might have a few snags. The first one is that there's this sender ID in here. And remember, this is the ciphertext I'm showing you. This is not the full message format with the envelope information, which of course has the sender, the receiver, the date, and some routing information on it. This is just the encrypted point part of it. And that itself includes who's sending the message, which doesn't make much sense because you can't read that until you've decrypted it, and after that, you've already had to validate the signature to do this, so you don't need this information in here. And Apple actually is trying to save space, so why are they wasting these bits? And it turns out, right, the worry about this might is well placed, because if you mount the identity misbinding attack I just articulated earlier, the system will reject the message, because the ID on the outside of the envelope that I replaced with my signature on it won't match the ID on the inside that's encrypted because I haven't changed that. And so Apple rejects the message. And this, I think, is because some clever engineer realized that there was an identity misbinding attack and added a countermeasure. Well, that's really unfortunate. Except for one point. They weren't quite clever enough, because remember the problem about ciphertext variability? This is in the ciphertext. It's not in the OEAP part of it if the message is long enough. And so we can just flip the bits in it, right? We know what it is, we know the value, and so we can actually flip it to be my ID instead of the attackers, instead of the senders, rather. And then this countermeasure amounts to nothing, right? Because it will correctly have the information on both sides of the message, and it'll validate. So this is just an annoying speed bump, but it's interesting nonetheless. Okay, so we still need a format oracle, right? We could mess with the actual binary plist, but that's compressed. So maybe it's better that we target the compression itself, because that's the next layer of the onion. And if you start doing that, well, what is the compression format? It's Gzip. Gzip, for those of you who don't know, is basically a header, a compressed data stream that's compressed with deflate, which is the actual compression algorithm, and then a COC32 over the decompressed data. And of course, when you get the message, you're going to decompress the data, compute your own COC32, and then check that it aligns with the one that was sent with the message, right? This is just how Gzip works in general. This is nothing special about iMessage. And this is problematic, right? Because we need to flip bits in here, and that's obviously going to change what the decompressed version is, and the COC is not going to align. So again, another speed bump. And if this was a cryptographically secure hash, we'd be in deep trouble. I probably wouldn't actually be able to give this talk because we wouldn't have an exploit. We just have an interesting observation of Apple didn't quite do things correctly. Luckily for us, unluckily for Apple, COC32s are actually, COCs in general, are quite malleable, right? It turns out that COC of A XORed with COC of B is equal to the COC of message A XORed with message B, right? Technically, this is slightly different if you want to deal with non-zero IVs, but it doesn't really actually change it. So it's not exactly clear what you do with this observation, right? Well, if we have a message that we don't know the contents of, and we have the CRC, which we also don't know, but we have the encrypted version of it, right? And we are flipping a bit in the message, and we represented that by XORing another vector in with the bit set to high that we want to flip, right? This is basic XOR. We do know the COC of that thing that we're flipping, and it turns out that we can, based on this exact equation, get a CRC on the valid mutated message, even though we don't know the contents of the message and we don't know the original CRC, because we just XOR in the CRC of what we're flipping, plus actually the length of the message in all zeros, because it's a non-zero ID, XOR that in to the encrypted CRC. And because the encryption is just done via stream cipher, when you decrypt, this actually persists through, and the CRC validates. So, okay, we've avoided another speed bump. That's good. But there's a problem that we still need a format oracle, right? And in fact, luckily for me, what I just told you is not quite accurate. It's a little more complicated, because remember, we're decompressing this thing that we XOR together and flip, right? And that means that the bit you're actually flipping might move, right? It might even flip multiple bits. And then we don't know the CRC correction to actually do. The reason for this is that deflate, which is what's used, uses Huffman coding, right? And so there's a static, for small messages, there's a static Huffman table that is used to encode all these symbols, and it's done by frequency. And so if you have, say, E, I, and H in these things, and given some relative frequencies, flipping one bit in the Huffman symbol is going to get you the next similarly frequent symbol or something, right? And that might not actually be the adjacent one in ASCII space, right? So the bit you flip here is not actually, when it decompresses, the bits that actually change. And this makes our lives more complicated, but it actually is a good thing, because this means we actually have a format oracle we can use, right? We can actually learn the contents of the message based on the CRC correction. The way we do this is we guess what the character in the message is, we flip a bit in the ciphertext, and we guess what the resulting change was in the decompressed message, right? And that guess is probably going to be wrong on both counts. So we try again, and eventually, after far more than 3, actually, you will probably guess correctly, and you will now have some idea what the contents of that message, that character in the message is, because you actually know that the CRC is valid. You repeat this a couple of times to deal with false positives, and then you can move on, and you can do this iteratively over the entire message to discover the contents, right? And so this is the basic trick. We're using the fact that Gzip errors if the CRC is invalid, and that we can actually make corrections to the CRC to validate what's going on, to validate the message. So just a second, for those of you following along at home, this is not a compression oracle, right? Compression oracle is a partial chosen plain text attack that leverages the fact that you can just, on any generic form of compression, doesn't matter how it works, you can look at how the message size changes if you put in maybe guesses as to what the other part of the message is. We can't do that here. We're doing a chosen ciphertext attack, and it actually only works for a specific type of compression, which is Gzip with a Huffman encoding. So they both use compression, but they're completely different attacks, just to clarify. All right, so that's nice. We now have this format we can exploit. We have the technique. We call it a Gzip Oracle. But we still need to be able to observe when that works, right? We need to see if this works or doesn't. And that's a little hard, because iMessage is not nice enough to send you errors when you send someone a message that doesn't work, right? It doesn't say, I'm sorry, your message could not be delivered, invalid CRC, please try again. And so we need something, right? There are read receipts, right? If you send someone a message, you can tell if they read it. That has 2 problems with it. First of all, it requires that someone actually is there to read the messages, right? Which they might not be. And second, we're going to have to send a lot of messages. And so if you see 2 to the 10 or 2 to the 18 messages getting sent from someone, the game's probably up. So we're trying to do a realistic attack here, and that's sort of a complete non-starter. So we need something else. Luckily, it turns out that if you send a large message in iMessage, or if you send a message with a video or a photo as an attachment, Apple's push notification network, as we saw, is sort of space sensitive. They don't want to send that. So instead, they upload it to the iCloud, encrypted under a symmetric key, and they send you a brief notification, which is effectively, hey, you have mail at this URL with this key to decrypt it. And then when the phone gets that and decrypts and decompresses the message, it does a download to iCloud, and it does a request to iCloud and downloads the message. And the cool part is we can observe this. And we know if we see this request that our message was correct. And if we don't see the request after some timeout, we know that it failed. And so now we have our error oracle. We can observe this remotely. It actually gets better. We don't, remember how I said we wanted a stealth attack? We can block the response to that request from iCloud, and then you can't download the attachment. And it turns out that iMessage fails silently in that case, right? It doesn't display anything. It doesn't display question mark, broken Unicode box or anything. Nothing. You never see the attack happen. And so we can do this entire thing stealthily. More interestingly, we can actually do this even if we can't observe this request directly, because we can mutate the message and make the request not go to iCloud, but go to an attacker-controlled server, say, i8cloud.com, which, fun fact, Matt actually registered just as a proof of concept. And so yeah, this is nice. This is the attachment message. It's a little big, it's a little complicated, but you can see that there's a key in there that we probably want to read out. This is what the message is encrypted under, so if we can read this out of the message, we can decrypt the attachment. There's also the URL that points to where you're downloading it. Unfortunately, this message is a little big, and so the attack gets a lot harder, because Gzip, it turns out, remember I said it uses static Huffman tables? Well, that's true if the message is small. If the message is large, it dynamically computes a Huffman table based on the frequency of the characters in the message. And this message happens to be large enough for that. And so this is a problem because we can't do the COC guess and check attack when we don't know the Huffman table. And so this is actually the hardest part of the attack. It's the most expensive part of running it. We have to somehow recover the Huffman table. And I don't really have the time to go into the exact details. It's a pain. You basically have to leverage the same COC error issue, but do it on known plain text and do some complicated stuff to search for edges between variable length symbols. Right, so once you have that, the attack is fairly straightforward. You get a message somehow. You change the sender ID, you use the COC guess and check attack, both to recover the Huffman table and then to read out the attachment key, right, this key right here. And then, given that, you simply decrypt the attachment message that you've downloaded from iCloud. Right, so we did actually implement this. It takes 2 to the 18 queries. And remember I said you have to wait when you make a ciphertext, you send them all from ciphertext to see if you get this request. Well, usually that happens pretty quickly, like 390 milliseconds. But you have to wait to make sure if you don't see it until you're sure that it actually failed, that's not just being slow. And unfortunately, there's some variability on this. There's a very long tail. And so the maximum we have to wait is a second, right? And so on the naive proof of concept code where we just wait to see this, we have to space every query out at 1 second. And so that takes 73 hours. If you improve on the code and you do backtracking where you send in a bunch of messages at once, and then leverage the fact that most of these are not going to require trigger requests, most of them are going to be bad. And then when you see a request, you can backtrack over the last 10 that you sent in to find out which it is. You can do this a lot faster in about probably 35 hours. But in either case, we actually executed the attack with proof of concept code against a real system. And we recovered 232 out of 256 bits, which is pretty good. You can brute force the rest of them. But of course, this is on one sample ciphertext that we just happened to pick. And so maybe it's not clear if this attack actually works, in general, but unfortunately we can't easily test it a bunch of times. So instead what we did was we wrote an emulator that emulated how iMessage validated ciphertexts. And we actually tested that against the real implementation, and then we ran a huge number of about 10,000 simulated attacks. It turns out that for about 34% of the time we recover all but 40 bits of the message. This encryption key that's in the attachment, and for about 23% of the time we recover all but 24 bits of it. So the interesting thing is if you plot the number of queries it takes versus the number of bits we recover, the attack is actually fairly efficient when we actually get it to work. But as you go down and start failing at recovering enough bits, it actually starts getting worse. So this tells me actually that the proof of concept code we wrote has some room for optimizations. So how do you fix this? Well, ideally, you deploy something like Oxalot or a Signal, which has forward secure properties and a nice system. If you didn't want to do that, you could use authenticated encryption, use AES-GCM or OCB mode, or just include an HMAC. But the problem is this breaks backwards compatibility, right? Because both ends of the protocol, both ends have to be upgraded, and if you have a billion devices and there's a bunch of different versions and a bunch of different things, that's a problem. So that gets us into the question of real-world mitigations. For those of you who've ever done that, this is kind of a tire fire. You're kind of trying to develop the smallest minimal band-aid that doesn't break anything, but actually does protect against the attack. Very briefly, we gave 2 proposals, one of which was to fix the identity misbinding attack that Apple had, but that was a little sensitive to how you did formatting and didn't work. The actual mitigation we proposed, which is what's deployed, is that you blacklist RSA ciphertexts, because the RSA ciphertext is inmalleable, so you're going to get this RSA ciphertext and then multiple versions of the AES ciphertext with bits permuted in it. And so if you see the same RSA ciphertext twice, you know that someone's mounting this attack, and you can just discard those responses. So this is deployed in iOS 9.3 Plus and OS X. It took Apple about 4 months and 30 engineers to deploy and test this because it takes a large amount of time to actually validate these things. And yeah, that's sort of, I have to give Apple a lot of props because while this was going on, at the end of it, they were dealing with this as well. So with that, I'm actually just going to take questions. Thank you.
Kenny Patterson from Royal Holloway. Thank you for the great talk, and I really appreciate the great work that you guys have done on this paper. I just wanted to point out that the solution is not really authenticated encryption. This is a public key primitive. What you really want is a signed encryption scheme, which you can build from authenticated encryption with the appropriate use of public key encryption and signatures.
Right.
And actually, if you look at the signed encryption literature, which clearly the Apple engineers manifestly failed to do, you find out that including the identity as part of the plain text is one of the countermeasures you need to prevent the identity misbinding attacks that you pointed out.
Right.
So what's really interesting here is that the crypto literature is very clear about how you should design a system to achieve the security properties that iMessage sets out to have.
Right, and so I think one of the interesting things, someone once asked me when I was giving a talk on this, like, why do we have this weird mix of RSA and ECDSA for primitives, right? You'd think if you used ECDSA, you'd use some fancy, algomol, whatever, elliptic curve algomol scheme. And I think the answer to this is this sort of was designed based on the menu of APIs that whatever cryptographic library they're using, I believe at the time probably OpenSSL, though not anymore, was. And those primitives just don't exist, as far as I know even, in implementations. So that's sort of, I think, how we ended up in this situation.
Juraj Somrovský, University of Bochum. So I would like to ask 2 questions about RSA. So have you tried Misbinding Oracle attacks against RSA ciphertext, like Miers attack?
So
RSA
as far as we can determine, this was RSA or EAP, and it was implemented correctly. So I think those attacks shouldn't be viable, but in all honesty, we mainly went for the vulnerability that we saw that we knew would have traction.
Okay, and the second question, so RSA OIP is statically defined, so you cannot do some backwards compatibility to PKCS 1.5, so that you could maybe execute Blankenbacher attacks?
You might be able to do that, actually. I'm not entirely sure.
Okay, thank you.
I also have one question. So when explaining the attack, you also said that you're dealing with false positives, but didn't go into details. Can you maybe elaborate on this?
Oh, sorry, the false positives what?
When you explained the decryption, so your actual attack, then you said that sometimes false positives can happen.
Right, so what can happen is, of course, you're not guessing as to what the actual character was and what you changed it to, you're guessing as to what the XOR of those 2 things were. And occasionally that can, of course, be valid for something else. And so what happens is you make a couple of more guesses as to the character was this, and I'm now going to change a different bit, and it's going to be permuted to a different symbol. And so if you do that 2 or 3 times, you get a fairly high assurance that it's the right guess.
Okay, let's thank the speaker again.